Hey everyone, welcome to another application of exponential functions. Today we're going to be talking about half-life. Okay, and you see half-life an awful lot. It's dealing with exponential decay. So really anytime you buy a piece of technology or a car, or when we deal with radioactive decay, this is all exponential decay, and it can be modeled by half-life. Okay, so those are just three very common ways we see half-life in the real world. So our first example, a student buys a new laptop valued at $1,500 when she arrives as a freshman. A year later, it's only worth $750. Okay, she wants to know how much, if this continues to depreciate at the same rate, how much should or would she expect to sell her laptop for when she graduates 4 years later? Okay, 4 years after she bought it. So we have our half-life formula here. Remember that a sub 0 is what we actually buy it for. So originally she paid $1,500 for this. So a sub 0 is 1,500. Okay, we're going to multiply that by the half-life. Now the half-life is just not said. Here's the half-life. It's actually right here. 750 after 1 year. That's not very good. That's actually pretty bad. So h is equal to 1 here, half-life, and t is going to be equal to 4 years later. So we're actually going to have 4 over 1, or just to the 4th power. So if we go ahead and calculate this, so if we take 1,500, okay, times 0.5, okay, to the 4th power, we're going to see the half-life. So after 4 years, she is going to expect to sell this computer for a whopping $93.75. I don't know what kind of computer you have. If it depreciates half after a year, probably a Packard Bell back in the day, right? Oh, right, Mr. Null? Oh, shots been fired at Packard Bell. Look them up on Wikipedia if you don't know what Packard Bell is. It's a doozy. Okay, second example. In our last example, radioactive isotope potassium. If we're science people here, I believe we write that as 42, and we get the cute little K for potassium. Okay, is used to diagnosis of brain tumors, and it has a half-life of 12.36 hours. If you have 500 milligrams of potassium and it's taken, how many milligrams will remain after 24 hours? So again, we're still going to look at a sub 0 times 1/2, okay, to the t divided by h, and so now it's a matter of substitution. Okay, so we had 500 milligrams, okay, times 1/2, and now you have to figure out your t value and your h value. Okay, your t value is 24 hours, okay, and you're going to divide that by that the half-life, which is 12.36. Okay, so there's our setup. If we wanted to go ahead and do this, we would have 500, okay, times, we're going to go parentheses 0.5, and then I will do this caret, and we'll do the 24 divided by 12.36. Now I put that in parentheses here so I can get the correct calculation. Be careful how you do that. Okay, you don't want to do 0.5 to the 24 divided by 12.36. It will do the wrong calculation. So I'll put that exponent in parentheses, and I look, and I get approximately 130. I believe it says round to the nearest milligram. Okay, so the nearest milligram, if our approximate answer is 130.15, the nearest milligram then would be 130 milligrams. Okay, after 24 hours, that's what would be left. So that's just a couple applications of exponential decay, and if you guys have any questions or comments, you can go ahead and type them below. We'll see you next time.